Okay, let's start. So the title of my talk is Accelerating Recurrent Neural Networks with Neuromorphic Principles. And my name is Chang. I'm from Delft University of Technology. Although the vast majority of the contents in this talk were generated when I was in University of Zurich and history. So I actually have one slide to introduce myself. I'm now assistant professor at the Department of Microelectronics at Delft in Netherlands since August 2022, and leading the lab of efficient circuits and systems for machine patterns. And this is the logo of our lab, where we are designing edge neural network hardware for telecommunications, video audio processing, healthcare, and robots. So you might be familiar with the application of neural networks in video audio processing, healthcare, and robots, but probably many of you didn't know how neural network hardware can be used in telecommunication. So I just show you a very simple example. So in 5G or 6G transmitters, the core component is a power amplifier. So basically it's used to amplify the modulated baseband signal to a high power so that can be broadcasted to the outside world. But the problem is there's a very high non-linearity, this kind of power amplifiers, and that will lower the efficiency of the whole system. So what people in the telecommunication field want to do is to add one single module in front of the power amplifier, basically a module to pre-distort the non-linearity transfer function of the power amplifier. So if you combine them together, you can fix the non-linearity. But the problem is the baseband RF signal is so fast. So usually if you are talking about 6G applications, the baseband frequency will be over 400 megahertz. So considering you have a sample rate of 400 megahertz, that's much faster than signals we're dealing with in video and audio processing. So that's, I would say that's a very good application of edge neural network hardware.
What would it do there, though?
Sorry?
What would it do? Why do you need it there? Would it learn to just undistort?
Well, it learns the what we are trying to do now is we first build a neural network to learn the non-linear behavior of the power amplifiers. Then we train a second neural network to inverse that non-linear behavior, and then we cascade them to the non-linearity. But in today's talk, I won't talk about that. I'll mainly focus on the acceleration of recurrent neural networks, and we'll mainly focus on real-time applications, such as speech recognition and autonomous driving. So they require fast sensing and processing to provide instantaneous response to the users or to stimuli from the outside world. But how fast is fast enough? So if we look at the speech processing task, the human nervous system can process sound within 10 milliseconds and can sense separated sound sources once the delay is around 15 milliseconds. And moreover, the reaction time of humans is around 250 milliseconds on average. So the control system in a self-driving car, which is far more complex than a speech recognizer, should probably finish computations within a similar time window to ensure the safety of passengers. So to process the input data and give a response within such a short period of time, real-time applications need low latency, sensing and processing to ensure functionality and provide a good user experience. But achieving low latency is quite challenging because in recent years, deep neural net models are getting bigger and having more arithmetic operations. And for example, from 2012 to 2015, from AlexNet to ResNet 152, in order to achieve 40% top-line accuracy improvement over the original AlexNet on the ImageNet dataset, we have to sacrifice 10 times more arithmetic operations. And that means we need to compute faster to achieve low latency. So this is easier to be done in cloud service, where we have large power budget to support abundant computing resources. However, the recent trend is to offload the deep neural network computation from the cloud to edge devices, such as your mobile phones, to eliminate the communication latency and better protect users' privacy. And now we're facing another challenge, which is to also ensure low power consumption to provide long battery life. And here is a simple example. A powerful server GPU has over 200 watts power consumption, while the upper limit of our mobile phones is usually less than 10 watts. And the battery size is usually 15 watt hour. And of course, you cannot support a server GPU with a mobile battery. But even if we assume we can, and we drain the battery completely within 5 minutes, which is totally unacceptable. So the real challenge here is how to achieve high energy efficiency. That means we need low latency and low power consumption simultaneously. So in this research, we are interested in how to accelerate recurrent neural networks. So the classic ones include long short-term memory and gated recurrent unit. They are useful in processing time sequences and widely used in applications like speech recognition, machine translation. And the core computation of RNNs is matrix multiplication. And in this simple example, the left matrix is the weight, and the right matrix is the input. And every column of this right matrix is an independent input stream. So this type of neural network inference is called batch inference. So in this example, the batch size is 3, which means that there are 3 independent input streams corresponding to the 3 columns in this input matrix. And graphics processing units or GPUs are currently the dominant hardware platform in deep learning, and they can process multiplications between large matrices very efficiently because the weights can be reused across multiple inputs to ensure high parallelism. But the problem is there are usually very few parallel input streams in real-time applications. For example, the chip of your mobile phone only needs to process 1 microphone input to recognize speech commands. So the latency is determined by how fast the hardware can process a single input stream, which is also called online inference. And this is where GPUs are not efficient because it literally converts a matrix multiplication into a matrix vector multiplication, which is a memory constraint algorithm. And let me show you an example. The plot on the right shows the effective throughput of the hardware versus its power consumption. And we have a third axis called effective energy efficiency. So this is 1 giga operations per joule. This is 1 tera operations per joule. So the closer of the dot to the upper left corner, the more efficient the hardware is. And this is a GTX 1080 GPU having massive amount of computing cores and claimed 9,000 giga operations per second throughput with about 100 watt power consumption. However, in reality, it only achieved 30 giga operations per second throughput with a batch size of 1 running RNNs. And this is another GPU platform called Justin Nano, designed for edge AI applications, claiming 500 giga operations per second throughput with around 10 watt power. And in reality, it only achieved 3 giga operations per second batch 1 throughput.
Could you explain why?
Sorry?
Could you explain why?
Yes, I'm going to explain right now, actually. So the reason of this big performance drop is that in online inference, the RNN fetched from off-chip GDDR VRAM cannot be reused to provide enough locality to fully utilize all the arithmetic cores on the GPUs with a batch size of 1. So that's the reason. And what's even worse is that if we look at the power consumption of the DRAM axis, the off-chip memory power consumption can be up to 3 orders of magnitude higher than the power consumptions on chip. So the key to enhance energy efficiency is to reduce memory access. And in this work, we want to achieve higher energy efficiency in real-time inference of RNNs compared to the existing hardware platforms. And in the power domain of edge applications, we designed 3 generations of RNN hardwares, Delta RNN, HDRNN, and Smartus. And we use them in mobile applications like audio processing and robotic control. And in the power domain of extreme edge applications, we also designed a chip to realize ultra low power keyword spotting, which is useful for Internet of Things. And during the rest of the presentation, I will explain to you how we achieve better energy efficiency and how and why they are useful in solving practical real-world problems. So in this talk, I will mainly introduce the RN cost reduction methods inspired by neuromorphic principles. So for me, neuromorphic engineering is to use very large scale integration systems to mimic neurobiological behaviors of the nervous system. And because artificial neural networks are basically neural-inspired algorithms, and we're interested to explore neuromorphic principles to reduce the cost of RNNs. So in our human brain, we have around 10 to the order of 11 neurons. And we have 10 to the order of 14 connections between the neurons. And if we assume that the neurons in the brains are fully connected with each other, there should be around 10 to the order of 22 connections in the human brain. But the actual amount of synapses is far less than the theoretical number. So this observation reflects the truth that neuronal connections can be very sparse. And on the other side, the neurons transfer information to each other using discrete spikes with limited firing rates. So RNNs could also potentially have sparsity in time. So in short, RNNs could have sparsity in both space and time. And we first exploited the temporal sparsity to reduce the cost of RNNs in time. And based on this method, we designed two generations of RNN hardware. So first one is called data RNN, and second one is called HDRNN. And we demonstrated data RNN in spoken digital recognition and HDRNN in keyword spotting and robotic control. And after that, we finally combined the other dimension, spatial sparsity, together with temporal sparsity to reduce the cost of RNNs in both space and time. And based on this method, I designed a hardware accelerator called Smartus to process spatially and temporally sparse RNNs to achieve ultra-low latency inference. So now let's start with data RNN. So probably the most popular or widely standard method to realize efficient RNN computation is spatial sparsity, which can be used using a model compression. So this figure shows very famous model compression method called pruning, and it was an important work from Professor Zhonghan that made model compression a hot topic after 2015. So the method removes unimportant connections between neurons to reduce the redundancy of a neural network model and creates spatial sparsity in the weight matrix. And the result is that we can convert a dense matrix dense vector multiplication into a sparse matrix dense vector multiplication. And operations and memory access can be saved by skipping the zero operations. And in our work, we mainly explore another approach called temporal sparsity, which helps to save cost in processing temporal sequences. So the method to induce temporal sparsity is Delft network, first proposed by my previous colleague, Daniel Neil, who was
also participant in Telluride, and also winner of the best new Neuromorphic. Daniel Neil, you guys remember him? Jerry remembers.
I remember he was here in probably 2015 or 2016. Yeah. So in this method, we set a threshold to gauge the activation change of the RNN neurons. So if the activation change is smaller than the threshold, we simply deactivate this neuron, and vice versa. And to compute this activation change, which we call a delta vector, we must buffer the previous state of the input vector xt-1 and subtract it from the current state to calculate this delta vector. And using this method, we convert a dense matrix dense vector multiplication into a dense matrix sparse vector multiplication. And the temporal sparsity in the delta vector helps us to save whole columns of computation and memory access. So the matrix vector multiplication output is MT, which should be added to the previous output state mt-1 to get the exact same final results on the left side. So there are, of course, overhead of using this method. So we must buffer and update two previous state vectors at t-1 and mt-1.
Was this applied to, or like the inputs to every hidden layer?
Sorry?
Was this temporal responsibility applied to just the input or every hidden layer's activation?
Both.
What's the question? Can you repeat it?
So the question is whether this delta mechanism is applied to both the input of the network or the hidden states of the recurrent network. So what we did here is we apply to both of them, but you can definitely change the way you implement this delta network according to the difficulty of your task. So for example, if you are doing a regression task, so probably you want to lower the threshold for the input of the recurrent network.
It's a minor point, but
Yeah.
it's not that you just have to sum the previous value and current value. You have to integrate.
Can you repeat the question?
I don't quite get your question. Sorry.
So it's not that you just sum the previous value with the current value of your output. You have to integrate, but it's an integrator, not just a.
Yeah, of course. Yeah, you have to integrate over the previous outputs of your network. That's what. Yeah. So basically, if you set threshold to 0, this delta network will infinitely approach the original recurrent network. If you have a higher threshold, so you are basically running an approximation. So, so we just talked about the overhead, so which is you have to buffer the xt-1, mt-1, and also you have two extra operations, one subtraction and one addition. But if we have large enough, high enough sparsity in this delta vector, we can save a huge amount of operations and memory access in this big matrix, which is much higher than the overhead. And another very nice feature of this method is that we have a very structured sparsity pattern. So it turns out in general purpose processors, it's quite difficult and expensive to find the locations of the 0 elements. So you might think, oh, well, okay, if we have a sparse matrix with a lot of 0 elements, we can automatically skip all those zeros to achieve good speed up. But in fact, it's not the case. It's quite expensive to find the location of the 0 elements. But here we have a very structured sparsity pattern. So basically, we only have to find the location of each column, and then we skip the whole column. So it can be much easier to be implemented in hardware. So this delta network algorithm was evaluated on a speech recognition task. So this plot shows the theoretical speedup and accuracy versus the delta threshold at test. So with a higher threshold, we can achieve a higher speedup while worse accuracy. However, the accuracy drop is slow with a small threshold. So for example, we could find a point at 0.2 threshold where we could achieve 5.7 times speedup with only 0.6% accuracy drop. Well, you may ask, why don't we just use activation sparsity? And here is a brief comparison. So the red plot is the theoretical.
What does that mean, activation sparsity?
Well, the way we induce sparsity in the vector is by subtracting the current state from the previous state. And if you're running a task with a lot of autocorrelation in the input data, the delta value can be very small. So a lot of the delta value will be very close to 0. And by setting a threshold, you can create a very high level of sparsity. So we extract the sparsity in this delta vector. But some people just do it directly on the X vector. So that you can set a threshold and set all the below threshold value of the XT vector to 0. By doing this, you can also create a very high level of sparsity.
Just like a relative.
It gets like a relative, yeah, exactly. So in this slide, I want to explain why we want to use the delta to induce threshold instead of directly using the state. And here is a simple example. So this is the formula to calculate delta. As you can see, we set the delta, so we preserve the delta value if the delta is larger than the threshold. Otherwise, we just set the delta to 0. And on the right is the way to induce activation sparsity. So you don't calculate the delta. You directly set a threshold and apply it onto the state vector. And if the state vector elements is below threshold, you set those states to 0. So it's a brute force. So if you look at the right plot, it is a theoretical estimated computation reduction on an LSTM RNN in a speech recognition task with activation pruning or state pruning. So this is the theoretical reduction of the computations. So the right value in the parentheses. So you can see this, the maximum theoretical operation reduction is just 2 times. And according to their paper, they have very bad accuracy drop according to our method. Sorry, compared to our method. So that's the way. That's the reason why we want to induce sparsity in delta vectors instead of directly on the activation vector.
Quick question.
Yes.
But for the delta vector, why do you set it to 0? I mean, you could also just accumulate the deltas and only send them when they're above the threshold. Because this way you lose information, right? If you just accumulated the deltas until they are above the threshold, you wouldn't lose anything.
Yeah, I think that's a really nice comment. So you can actually find an implementation of the method you proposed in a recent paper in CVPR 2022. So there's a paper called Delta C. They use a very similar name to our Delta R.
Okay.
So they implement exactly the same method you just talked about.
Yeah, it seems like it's already accumulating something, right?
It's already accumulating, but if you have a high threshold, you are throwing away a lot of information.
Yeah.
The higher the threshold, you throw away more information. Yeah. But by doing this, you can definitely induce a higher level temporal structure, so that you save more during the computation. Is that clear? I go to the next slide. And based on this method, we designed our first FPGA-based RNN accelerator to exploit temporal sparsity. So the name is Delta RNN. So the accelerator has an input encoding unit to calculate delta vectors and encode them into a non-zero value list and non-zero index tree. Pretty straightforward. And non-zero index is used by a controller to fetch RNN weights from on-chip memory. And weights, together with the scheduled non-zero values, are fed from the matrix vector multiplication unit to handle the matrix vector multiplication. And to accommodate the computational pattern of the dense matrix sparse vector multiplication, because after you're removing all columns, your weight matrix becomes very tall and thin. So to accommodate that, we arrange our processing elements along columns and broadcast the non-zero values to their corresponding processing elements. And at the end, we use an activation pipeline to process the matrix vector multiplication results to generate the final outputs. And we benchmark this hardware on an audio processing task to recognize single digits from 0 to 9. And the plot shows the average vector occupancy and the hardware speedup versus the delta threshold. So the occupancy is the ratio of non-zero elements in delta vectors. And by increasing this threshold from 0 to 80 in hexadecimal, so in decimal, it's basically just 0 to 0.5 in floating point numbers. So you can see that the delta activation vector, the vector occupancy, reduced to 57% and 2% for the input and also hidden states, respectively. So this reduction of arithmetic operations helped us to achieve 5.7 times speedup over processing a dense recurrent unit. And we compare the performance of delta RNN to the previous state-of-the-art RNN accelerator, ESE, which was designed to support a batch size of 32 and achieved 2,500 giga operations per second effective throughput. But the problem is, without the weight reuse opportunity that only existed in large batch inference, the batch one effective throughput of ESE reduced to just 80 giga operations per second. So because the external memory bandwidth of their hardware can only support up to 32 processing elements for each input stream. And in contrast, Delta RNN architecture buffers the neural network models completely on chip to provide much higher memory bandwidth to process a single input stream. And by further exploiting temporal sparsity, Delta RNN achieved 15 times higher batch one effective throughput versus ESE, which is the leading batch one performance with similar power consumption. Yes, please.
Do you have an estimation of the cost and accuracy? Because I guess you're losing some information, right, in this method?
Yes, so we show the accuracy drop of this method. This is the figure in which we evaluated the performance of Delta network.
Okay, sorry.
So we actually also have more results in our hardware paper, which we evaluated on a simpler task to recognize digits from 0 to 9.
Okay.
Yeah, if you're curious about the results, you can check our hardware paper also. Okay, so let's, okay, I'm going to talk about the demo of this Delta RNN, in which we build a spoken digit recognition system. So we want to achieve a continuous spoken digit recognition, which means that the system should recognize long sequence of digits. So we first design a Nyquist sample system based on Delta RNN, which uses a traditional microphone and requires an analog to digital converter and fast forward transform module to extract audio features in the frequency domain. So the left figure shows the FFT-based audio feature, which is a spectrogram with multiple frequency bands distributed in type or frames. And we also built another system called an event-driven system using a spiking cochlear as an audio front end. So the human cochlear has the vestibular membrane and at its core. So the sound of different frequencies will induce mechanical vibrations at different locations on the membrane. And the membrane will convert this mechanical signal into an electric signal and send it to our brain. So the spiking cochlear mimics the functionality of human cochlear and has multiple channels to extract sparse spiking audio features directly in the time domain. So using a spike count module, the accumulated spikes of each channel within the frame are sent to the Delta RNN for classification. So the benefit of this event-driven system is that you get rid of the analog to digital converter and also the FFT modules, so that you can save latency and also power consumption. And here is the demo video of the Nyquist sample system. So in which we have test speakers from the UK, France, Canada with different accents. So now I just show you this video. Yeah.
2, 1, 3. 07737729834. 5, 2, 1, 3, 6, 7, 8, 9, 10. No, 10.
Here's a demo video of the event-based system. And I will just play the video since told me back in 2019 we will give you a very good explanation. The video.
Let's fast forward and Chang, please. RNN hardware accelerator to do audio digit recognition. And the silicon cochlea mixed signal chip is here. It has 2 microphone inputs left and right that are not really used in this demo. And the spikes from the silicon cochlea, from binaural silicon cochlea, are visualized here on this laptop over this USB interface. They show, these dots here show the spike events as a function of time and frequency channel. So if I make a tone, for example, a high tone, the spikes are quite closely spaced. Or if I could make a lower tone, oh, you see how the spikes are spaced out further in time? And they're tilted over like that because there's some delay going along the basilar membrane as you go from high frequency to low frequency. Anyhow, in this demonstration, these spike events are only triggered when there's sound. And they give you kind of a spatio-temporal representation of the sound that's data-driven. The key point of that is that these spikes now can do a data-driven input to this change-driven delta recurrent neural network hardware accelerator. So the recurrent neural network only does inference when there's sound output from the silicon cochlea. And in this demonstration, the Delta RNN FPGA accelerator is only doing the inference when it's getting changing sound input from the cochlea. Now, in this demonstration, it was trained on this kind of data from the silicon cochlea, and it's trained to do audio digit recognition. So I'll now try to demonstrate that.
First try to fail.
9, 4, 8, 7, 0, 2, 1, 5, 6, 7, 8, 8, 8, 8, 7, 6, 5. Yeah, that works okay.
Error also again. You keep trying.
All right. So, taking the Hey, hi everybody, this is Toby Delbrook. I'm gonna
Why I cannot. Okay.
that's where it's responsible.
Okay, I think I have to skip it. Okay. Okay. So let's do a summary of Delta RN. So Delta RN was the enable the later points. So Delta RN was the first RN actuator that exploited temporal sclerothy and achieved a lead in benchmark effective throughput than previous works. And we had a successful demonstration with eventual sensor. But the limitation of this work is that the model size is limited by the on-chip memory. Because the network, we have to make sure the network size is less than 1 megabyte. And also, we have a very high wall clock power, around 15 volt. So that is not ideal for edge applications. And that's exactly the reason we start our next project to design the HDRN accelerator. So before 2020, RN accelerators, including the new state-of-the-art at that time, BBS, all focused on achieving higher throughput without considering too much on reducing the power consumption. So the BBS use a model compression method to compress a large LSTM RN network from 6.4 megabyte to 0.8 megabyte. And by buffering this 0.8 megabyte network on a high-end FPGA and exploit spatial sclerothy, the BBS achieved 2.4 tera operations per second background throughput, doubling the performance of Delta RN. But the problem is 0.8 megabyte is still a large number for low power edge devices. So if you look at all those low power microcontrollers, the on-chip SRAM size is usually just several hundreds of kilobytes. So to achieve their best performance, they had to spend a cost of over $4,000 with a power consumption of 19 volts. And in our work, we switched to another direction to explore whether it's doable to run large RNNs faster on resource-constrained edge devices. So we call this new accelerator HDRN, which still exploits temporal sclerothy, but this time it will be implemented on a low-end FPGA that can be powered by a battery, and it has much lower cost with just $90. So the HDRN accelerator relies on fetching weights from 512 megabyte of-chip memory, in which you can buffer much larger models. And in contrast to Delta RN with massive amount of processing elements, in fact, it has around 800 processing elements. The HDRN only has several, in fact, only 8, 100 times less processing elements in vector array for tiny edge platforms. And we made the architecture scalable to fully utilize the SCAR's off-chip memory bandwidth and supports variable model size. And of course, HDRN exploits temporal sclerothy to realize acceleration by skipping unnecessary operations and memory access. And we implement HDRN on a tiny edge platform called MidLab. It has the smallest link FPGA you can find on the market and has only 0.2 megabytes on-chip memory with around 2 watt power consumption and a very low clock. And we evaluate the effective throughput of HDRN and accuracy of the temporal sparse Delta network on a continuous spoken digit recognition task with a much bigger model size of 5 megabyte. So the dashed line is the baseline hardware throughput without temporal sclerothy. And the blue curve is the accuracy in word error rate. And the red curve is the effective throughput. So similar to the previous results of Delta RN. So increasing Delta threshold leads to higher effective throughput and worse accuracy. But we can find optimal points where we can achieve a balance between throughput and accuracy. And at this point, HDRN achieved 20 giga operations per second batch-wide throughput, corresponding to 10 times speedup over the baseline. And of course, you can adjust the data, the delta threshold to realize instantaneous trade-off of accuracy versus latency according to the need of different applications. We compare the latency of HDRN versus other commercial edge AI platforms running the same task, including a Jetson Nano, Jetson TX2, and also a powerful desktop GPU, GTX 1080. So on average, the 2-watt HDRN achieved 0.2 millisecond latency, which is on par with the nearly 100 watts GTX 1080. But of course, you can see a higher variation of the latency due to the dynamic temporal circuit. And if you compare the latency to the edge platforms, HDRN achieved around 5 to 7 times better latency on average. So here is a summary of the performance of HDRN against prior art and commercial edge AI platforms in RN computation. So the previous RN accelerators like ESE and BBS, they were not designed for edge inference. And that's why we normalized their performance to the same frequency and same number of Mach units. And compared to ESE and BBS, HDRN achieved at least 4 times higher power efficiency. And we also compare HDRN to the commercial edge AI computing platforms, and HDRN achieved at least 5 times higher power efficiency compared to these platforms. And we first demonstrated HDRN keyword supporting task to show that it can support such a task with much lower power efficiency. So here is the video showing exactly the same demo of computer spoken digital recognition. So let me first play a little bit of this video. 2, 6, 7, 8, 9. Okay, I think that's good enough because it's the same thing, right? But you can see the setup is much smaller, and they can be powered by a single USB cable. And we attach a USB power meter on the laptop to show that, to prove that the power consumption is just 2 watts. But besides that, I don't just want to show you the recorded video. I want to show you a live demo. Because yesterday I found out the demo project in my code mountain, and I really want to try to run it again. And let me see. Let me share my screen. I hope it runs okay. It's not working. Okay. Action. Okay, now it works.
And you can hold it up, or is it down?
Yeah, so here at the board with a small microphone, because the same setup you saw in the video. But I don't think it's running. Huh? Is it running? It's running. Okay, let me try. Okay. 1, 1, 2, 2, 3, 4, 5, 6, 6, 7, 7, 8. Okay, probably something wrong with the I don't know. This is demo effect. Wow, if you try this demo later on this laptop, it performs much better than this. Let me try again. Okay. 1, 2, 2, 3, 4, 5, 6, 7, 8, 9. Okay. I promise you it works much better than this. If you want to try, you can try this after this stop. 1. Articles. So this is actually a very simple demo. Basically, you can do the same thing on your mobile phone. The main purpose here is to prove that this delta mechanism can really run such a network to recognize some digits with very low latency. Now I continue my talk.
So you don't have a spiking copy anymore for the edge?
Which one? Well, yeah, for this one we don't have a spike. It's basically using a microphone. By this one, this is a Pico mic 3.
And where's the spectral computation done?
Where's speaker extracted in the article? Because yes, in CPU. Yeah. So theoretically, that's something we can also implement in FPGA to further lower the latency.
Hey, Chang, the previous case, well, the comparisons were only against GPUs that are meant to be handling much larger batch sizes.
Yeah,
What's the question?
Again,
it's not finished yet.
again, was that just because there was an absence of chips that accelerated single batch size?
Yeah, I would say so. Yeah, if you look at the latest neural network accelerators published in the best conference ICC or.
What's the question? I don't want to hear the question.
Okay, the question is it so probably repeat your question again?
All of the comparisons were against GPUs that are made to handle much larger batch sizes. Was that just because there's no other comparison point in existence? And yes, it's yes.
But then I have to jump in like a bit theoretical statement maybe, but we were also looking at like audio applications and so on, and there are companies that claim to have chips that do pretty much exactly this, like keyboard spotting in the milliwatt range and even microwatts. And so the question is like, is it a good comparison, like to compare, right?
Yeah. That's a proof of concept.
Yeah.
We also built like microwatt level chips, which I'll show you later.
Yeah.
So the question would maybe be like, what is the limit what this chip can do at the power point of like 2 watts?
Yeah.
What can you actually do with it that maxes out the performance of the chip?
Okay, so probably I'll show you in the next demo. So we have another demo after this to show you the capability of this hardware to do something maybe more challenging than keyboard spotting. Okay, so before showing the next demo, I have some slides to talk about. So after evaluating the performance of HDRN, we further analyzed the power consumption of this platform and found out that the core logic of HDRN only consumes 87 milliwatts, which is only 4% of the whole system, and the majority of the energy was consumed by the ARM CPU, the dynamic memory, and other off-chip components. So it's a complete waste. So this result inspired us that if we can implement an RN accelerator similar to HDRN in pure integrated circuits without relying on FPGAs, we might achieve something much more energy efficient and realize a similar function at the extreme edge. So after this work, we integrate an RN accelerator and an event-driven sensor on the same chip. And in this work, Dr. Pandit Kim, who was a postdoc in the sensors group, he was responsible to design the analog part, including the sensor and also solar energy harvester. And I was responsible to design this RN accelerator. So for this 65 nanometer keyboard spotting chip, we train a small RNN with only 24 kilobytes of parameter. And it can recognize 12 keywords with 86% accuracy. So the network can be completely buffered in on-chip memory. And by ensuring a close proximity between the data and also the processing units, we could achieve a real-time keyboard spotting with only 23 microwatt power. And if you look at power consumption of the RN accelerator, it consumes only 10 microwatts.
What clock? How fast was it running? Clock frequency.
It's tunable, but for this number, we run the chip at 250 kilohertz. That's already good enough to run this task in real time. Yes, please.
Yeah, maybe you're going to talk more about it, but is the data matter actually a good fit with event-based like data?
No, this chip is not even running a Delta network. It's running it's running a dense recurrent neural network.
Okay.
Yeah, we haven't implemented the Delta network in ASIC. Yeah. That's our future work.
So
yeah, yes, please.
what's the rationale of putting the energy harvester for this?
So that the whole chip has
You got the paper accepted.
That's not only answer. But at least if you have the solar energy harvester, you can at least power the on-chip part solely by a solar panel. Yeah. Of course, you cannot power the whole PCB with the solar panel. That's impossible. Okay, let's continue. So we also evaluate HDRN in a robotic control task. So in this project, we collaborated with Dr. Richard Galhart from Caltech, who is working on control series of robotic processes called Advanced Mechanical Processes 3, or AMPRO 3. So it's helpful to improve the life quality of amputees by increasing their comfort and reduce the energy required through local modes. So this robotic process simulates human legs by using two motors to model the knee and also the ankle, respectively. And in this control system, we need a mass model to generate the desired trajectories of the knee motor and the ankle motor. And we also collected the actual trajectories from the two motors and compute their error between the desired and the actual trajectories. And then we train an RNN controller to directly generate the torques applied to the target motors, the knee motor and the ankle motor. So to train our RNN, we collected over 300 seconds of flat ground walking data. We trained a two-layer delta GRU network with 128 neurons per layer. And the main challenge here is to achieve a low latency to catch up with the 200 Hertz sensor sample rate, corresponding to 5 millisecond latency. So thanks to the small size and low latency of HDR on Minitab, we can power the accelerator board with a battery attached onto the processors. And here is the demo video of this project. Let me play it. Yeah, let me explain it. So you can see that it's the knee motor, this is the ankle motor. We have our HDR board attached onto the processors. And we also have a mobile phone battery bag attached here to power the board. And the HDR board is connected to the microcontroller on the processes, which I will explain later. So in the next slide, I talk about some of my personal experience. So this process control demo was actually built back in Telluride 2019, where we spent a lot of effort to make our first prototype working at the beginning of the third week. So in this figure, you can see left side is Antonio, and right side was me. And but unfortunately, the circuit board of the processors burned out just 2 days before the final demonstration, and where we didn't show a successful HDR control walking. So on the right, I want to show you a failure video during our development.
You guys recognize it?
This is Rachel.
Ready?
Rachel actually fell down several times. So every time I updated the recurrent neural network model, she was responsible for testing it on the processor, and I couldn't always make sure the recurrent neural network worked properly. So sometimes the lag just got cramped. So it was actually quite dangerous to test this process. So I remember that we spent another 3 months after the workshop, and we managed to solve all the problems we had during the workshop. And finally, we had a paper accepted in April 2020. So finally, I want to show you the system architecture of this work. So the figure shows the system architecture, the knee motor, ankle motor, and the position and velocity sensors on the Emperor 3 are managed by a Big Bone Black microcontroller. And we connect the Minitab to the Big Bone Black via SDI interface to transfer sensory data and control signals between the two sides. So basically, in this work, the Big Bone Black is only responsible to move data. It's not used in any computation. So we only find one previous work that had a similar setup to our work. And they use this setup to do an RNN gate phase estimation on an exoskeleton. They run a tiny LSTM with only 16 neurons in total on a half-kilogram computer with tens of watts of power consumption. And while in our work, we use RNN directly to control the robotic processes. And we are using a much larger neural network with 128 times more operations. And all the computations was done on this small form factor battery-powered mini-LED board with 2 watt power consumption.
So what was the actuator power? Like how much, does that 2 watt include the actuator power as well? Or?
So the 2 watt is everything on this FPGA board.
Yeah. Including the actuation of the robotic prosthesis, or?
No, not. 2 watt is just the processing power of this board.
Do you know how much power the prosthesis takes? Like
For the prosthesis, I think it's over. Instantaneous power can be up to like, if I remember correctly, like 40, 50 watt. That's definitely not possible to be powered by a mobile phone battery pack. So
This AmPro is a very early prototype. You would never, no patient could ever wear it. It's much too heavy. It's a research prototype. Right. So it's definitely for research. But all this stuff is advancing tremendously because of bicycles, right? Just like the Wright brothers.
Sorry, what?
Yeah, no, the Wright brothers. The first
okay.
that was enabled by bicycle, praise for bicycles. Same thing's happening now for prosthetics.
Okay, to summarize.
Bicycles.
there is flywheel control where you can recover the energy from the.
I'm not sure. I don't know anything about that. Yeah. I don't think it does energy recovery, but it should be on.
Okay, now I continue. So to summarize, HDR achieved 5 times quicker speed up than a paired commercial edge AI platform on continuous spoken data recognition. And also HDR won the overall best paper award at the AICAS 2020 conference. And on the application side, we approved the usefulness of HDRN in solving robotic processes control.
Chang.
Yeah.
At least 5 minutes.
5 minutes, okay. So at this stage, so we were asking ourselves what's the next step. So our answer was to develop new methods to further reduce the cost of our computation and design hardware to achieve faster inference. So let's move to the design of Spartus. So I will try to be faster. So our previous method only exploited temporal sparsity, but the problem is the model size is still big. It's still the weight is still dense. So what we can do is that we can combine model compression with the weight pruning to combine the temporal sparsity and the weight sparsity. But it's not as easy as you think to exploit both temporal sparsity very efficiently. Because if the distribution of the weight of the non-zero values is irregular, you cannot efficiently exploit the sparsity. So how can we solve this problem? So the first question to answer is how to induce spatial temporal sparsity. So we designed a 3-step training strategy. The first step is to pre-train this LSTM model with a model compression method we developed, which is called a column balance calculated dropout. So assume that we have 2 processing elements along the column direction. We first assign interleaving rows to them as their workload. And then we set the same number of weight elements to 0 between the columns, and also between the processing elements within a column. And for example, in this sparse matrix, every column has 2 0 elements, and every processing element has only 1 0 element to skip within a column. So by doing this, you can make the sparse pattern structure. And the next step is to transfer this sparse LSTM weight to a delta LSTM model to induce temporal sparsity. So by retraining this delta LSTM on the same data, we can induce the sparsity in the delta. And the second question is how much does this method affect the accuracy? So we evaluated this method on speech recognition task on the timid dataset. So in this figure, you can see that the vertical axis is the phone error rate, which is actually the accuracy. The horizontal axis is the weight sparsity. So the dashed black line is the baseline accuracy without applying the pruning method. So by increasing the weight sparsity from 10 to the maximum, you can see that at the very beginning with small structure sparsity, the irregularization effect of the pruning method can actually help us to achieve even better accuracy. But if you push it to the maximum, you significantly lose accuracy. But you can find a point where you can achieve good compression ratio with good accuracy. And for example, we take this model, which has been compressed by 16 times, and retrain it on delta LCM, where we can also select the threshold without losing any accuracy. And next, we have to think about how much we can save from this spatial temporal sparsity. So as we saw in the previous slide, the spatial sparsity has already led to 16 times reduction in computations. And the left plot shows the temporal sparsity versus the threshold. So with 0.3 temporal sparsity, we could achieve around 80% temporal sparsity without losing accuracy. So it converts to at least another 5 times reduction in computation. So by further combining the temporal sparsity with spatial sparsity, theoretically, we should be able to reduce the cost by 80 times. And after we describe the method and we want to explain the design of hardware, but due to time, we'll probably skip it. So basically, we designed another accelerator to exploit this spatial temporal sparsity. And we implement this accelerator on a Xilinx Zinc 700 FPGA with 8 processing arrays and 54 processing elements per array. So 512 processing elements in total. And here is our final results. So the left axis is the effective throughput, and the horizontal axis is the threshold. So if you don't apply any sparsity, the baseline performance is 0.2 tera operations per second. If you use spatial sparsity, you can improve the performance to 2.8 tera operations per second. So that's 14 times speed up. And if you further combine the temporal sparsity, it leads to another 3.3 times temporality. So in total, we could achieve 46 times speed up compared to the baseline performance by using this method. And of course, we compare the performance as well as with previous state-of-the-art. So if we compare to ESE, with the same similar accuracy, we could reduce the latency from 82.7 microsecond to just 1.6 times. And if 1% accuracy loss is tolerable, we can even reduce the latency to just 1 microsecond. And if you look at the energy efficiency, we also achieved the highest energy efficiency at 1.1 tera operations per second per joule. So to summarize, in this work, on the software side, we explored 2 brain-inspired cost-saving methods. So I first evaluated the temporal sparsity on more tasks, and finally proposed a method to effectively and efficiently combine the spatial and temporal sparsity to have intensively reduced the cost of ARM computation. And on the hardware side, we developed Delta RN and HDRN to exploit spatial temporal sparsity to achieve higher effective energy efficiency than previous works. And also Spartus. And if you compare Spartus to the ASIC RN accelerators that also exploit sparsity, the energy efficiency of Spartus is still very competitive. So here are the plots of the ASIC accelerator also exploiting sparsity. And in the future, we want to implement Spartus in ASIC to chase even higher numbers in energy efficiency, so that it can be used to solve more complex AI problems with less power consumption. And on the application side, we use our hardware to solve practical applications like continuous spoken data recognition, keyword spotting, and also robotic process control. And finally, I want to talk about the limitation of our work. So the biggest one is that the performance of this kind of hardware, software, co-designed cost-saving method is model-specific and also task-specific. All the numbers we have reported in this work is only meaningful for this specific task and even specific model. So an obvious mitigation strategy is that we can evaluate our method to a wider range of network architectures and also applications. So that's our future work. And that ends our my presentation. Thank you. More questions?
So we have the HDRN here. In fact, you just got it running again, right?
Yeah.
That's what we want to use for the control stuff. We want to control the protocol with that.
Yeah.
Here.
Yes.
And you also have an edge Spartus design, don't you?
Yes, but that one is not ready for production. So that's why I still break this for you.
It's too kludgy right now.
Yes. So we're not easy to use. And the problem is I didn't have enough time to fix it.
You didn't really talk about this training method, which I think is really cool. This column balance targeted dropout.
Yeah.
It's just dropout.
Yeah.
But you always keep the columns balanced in it. How does it work?
So again,
It's key to this, right? To train this weight sparsity that's balanced across units. Is that right?
Yeah.
It's weight balanced across units. Sparsity is weight balanced.
yeah. So the target dropout is basically a method that you randomly drop weight elements from the weight matrix. So basically,
On every sample.
you can control the frequency. You do this target dropout, so you can do it every several updates or every epoch.
I think you're describing drop connect, which is different from drop out.
Yes, well, this one the method was actually published by one of I think either Hinton's student or Hinton's collaborator. So they published a method called target dropout, but that one is completely irregular. So what they did is that they said so every time they train a network, so after several updates or several epochs, they sort the magnitude of all the weights, and they then set a fixed percentage of the weights that has the lowest magnitude to 0, and they do that randomly. And what I did differently here is that I do the target dropout in a structured way. So basically, you pre-allocate the workload to the processing elements, and then you force the processing element to have a very structured data flow. So by doing this, you can get rid of the hardware arbiter, which can significantly simplify your hardware design. Hope that's
How many problems have you tried that on?
sorry.
I mean, you did this rather large Libre speech, speech recognition, right? That data you were showing from was continuous speech recognition, right?
Yes.
Spoken audio loop.
Yes, the result we show here is relatively simpler timid data set, but in our paper we also have results on the large scale Libre speech data set, 100 hour. So we also show that by using this method we can achieve a significantly speed up of the acoustic model without losing any accuracy.
But is it practical to do like multi-layer RNNs on the edge DRNN that have lots of weight units per layer? Is it practical?
Well, it's,
Like, could you do a 3 times 200 unit network?
yes, practical, because when we implement the network on the so this result I reported in this slide is actually running a 2-layer GRU network with 768 neurons per layer. So the total amount of parameter is over 5 million. So it's a quite large network. So it's definitely feasible.
Can you elaborate the structure a little bit more?
Yeah. Sure. So this animated again. So if you just do a very naive targeted dropout, you basically randomly set weight elements to 0, and that will result in a very irregular distribution of 0 elements. But what you can do differently is that you look at the architecture of the hardware. So let's say you have 2 processing elements in your hardware, which is calculating the weight along the column direction. So basically, let's assume though, in the first clock cycle, you calculate these 2 elements. Next clock cycle, you calculate these 2. And next clock cycle, these 2. And you can pre-allocate the matrix workload to your processing elements. And then you can design a structured targeted dropout algorithm to induce 0 elements in the matrix by forcing the numbers of 0 elements to be the same when you look at different columns. So every column has the same amount of zero elements. And besides that, you also have to make sure that every processing element, so the green color and the blue color, has the same amount of zero elements within each single column. So by doing this, the workload between different processing elements is strictly balanced. So there won't be a case that, okay, you have, let's say 10 workloads assigned to processing element 1, but you only have 1 workload assigned to processing element 2. Right? So theoretically, you have, so let's say 9 workloads for PE1, 1 workload for PE2, right? So theoretically, if you can evenly distribute the workload to the 2 processing elements, you should be able to finish it within 5 clock cycles, because you have 10 workloads, 2 processing elements, right? 10 divided by 2 is 5. But it's likely that if you have a irregular distribution of the 0 elements, you can have something like PE1, 9 workloads, PE2, 1 workloads. And the whole thing finish will be within 9 clock cycles. So that's something we don't want. We want evenly distributed workloads among all the processing elements, and that's the motivation I designed this method.
And there's a second advantage is that this way you ensure that the mean is preserved during the dropout operations. So
there is the mean of the mean of the weights, or
mean weight magnitude or something? Mean what? I don't think that's what necessary, right?
well, if
I mean, it's not really, it's just normal dropout, right? You just make sure that when you do the dropout, it's balanced.
yes,
Right, and then you end up with something that's balanced in the end.
Yeah.
So that all the pressing elements, finish at the same time.
no, this is some backup slides I have. So this is what happens after applying this method. So originally, you have a weight distribution like this. And after you do the training with this target dropout method, you can see that a lot of weight elements close to the zeros will be deleted. But the overall distribution still looks like a normal distribution. But the problem is, the way the target dropout is done is that you first sort the magnitude of all the weights, and then you remove the smallest weights, right? And you will see that by applying this method, you will have an increase of the magnitude of the weight elements. Yeah, but of course, this method can be combined with something like a L1 or L2 regularization to limit the distribution, the mean and max range of the weights. Yes.
You were saying before that it's not very efficient to skip 0 connections, so it's not as easy to do as people might think, right?
Yeah.
If you have a very sparse vector and so on.
Yeah.
This is actually the last I'm not sure what to say, but we were last Telluride actually thinking about the asynchronous circuit that can faster than linear, somewhere between linear and logarithmic time to iterate over a very sparse vector. So ideally, if it's very, very sparse, it should be very quick at iterating over the indices where there is something. So maybe that might actually be interesting.
Yeah, sure.
Should talk about it.
Yeah, we can discuss that after this talk.
This might be a naive question, but is there a reason why you wouldn't just use a small network without sparsity?
Okay, so in our experiments, there's no way you can achieve the same level of accuracy by starting with a smaller network. So this kind of weight pruning methods works kind of similar to a circular optimal architecture of the network that can achieve better accuracy. So we evaluated this on the speech recognition data set, and also done a simpler keyboard spotting data set. We observed that if you start with a larger network and you set a relatively loose target weight sparsity, let's say just 50%, the sparsity, you can use this method to achieve higher accuracy. Yeah, by starting with a larger network.
So you didn't talk about it much, but the key thing here is that your on-chip memory is size greatly reduced, right?
Yes.
The idea is to use DRAM memory for the big weight matrices. Well, you hardly mentioned that fact that when you use DRAM, you have to schedule a read so it goes in burst mode. You hardly mentioned that. I think that's a really key advantage in terms of cost and
Yeah, sure.
It's chip cost and everything else, because DRAM is like nothing cheaper than DRAM.
Yeah, exactly. So the DRAM, so to mostly efficiently make use of DRAM is that you have to make sure the data access is in a burst mode. So basically you give a starting address and then you give a burst length. And you send that to the DDR controller to fetch data from the external DRAM. That will give you the fastest data throughput and also the highest energy efficiency. But the problem of irregular Sparky is that you cannot predict the location of the non-zero values. So if you don't do any encoding of your sparse matrix, or you don't have a very large area of circuits to predict the locations of your non-zero weight elements, you will have to force your DDR controller to run into a non-burst mode. So basically, every time you give it an address, and it only reads the data at that address, and that will make the DDR controller very inefficient. So that's another benefit of using a structured pruning method.
Anyway, we're over time. Thanks, Chang.
Yeah.
But the 1 o'clock we reverse, we have Paxon Frady.
Yes, hi everyone, I'm Paxon. I'm at Intel now, and yes, today I'll be telling you about this concept we call computing and superposition, but we're doing it in a more classical way. But yes, of course, have to the Tellurides, I have to get to cover me. But I also was an undergraduate at Caltech, and actually, I think I took Carbonese class, and if I remember correctly, Toby, you taught it when I was an undergrad.
I was a TA then. Oh, was no, you not there.
You were there, like just you kind of replaced Carver, I think. And,
No, that's when she did not did a sabbatical there.
right, yeah.
Yeah. You were one of the 5 students.
Yes.
Yeah.
So yeah, I've been part of this community and really inspired by Carver, ever since being an undergrad. And I think one of the big ideas that Carver has is that, like, you think about biology and how well the brain works, this use of physics was a huge important aspect, and taking advantage of kind of physical primitives.
You don't have to sell us on that, Paxton. Just go ahead.
Yeah. Okay, but then of course there's now quantum computing, and when I talked to Gert earlier this year, he invited me and was telling me about this group at the workshop, and I always get asked if like my work is quantum computing, and so it's kind of is, but quantum computing still, of course, relies on physics, and but there's sort of this special extra thing with quantum computing, and somehow through entanglement, you get this like exponentially growing representational capacity. And there's these grand promises of, breaking all these cryptography problems and all these things. And of course, like Google is claiming quantum supremacy, but there's a lot of controversy. And then, like very quickly, people were already debunking these claims. And even more so, there's a lot of skepticism in general about really if quantum computing can actually scale. And the reality might be that it won't work the way physicists say it will because of how noise works and the need for error correction. And so not only is quantum computing extremely difficult, this promise about exponential scaling through entanglement might not really be scalable and feasible. But of course, there's a long history of kind of using physics to solve computational problems. And this paper by Hopfield and Chang was one of the earliest examples of formulating a neural network to have an energy landscape and then using its dynamics to solve a problem like the traveling salesman problem and be able to solve these tough computational problems. And the question really that's been driving me lately is now that can we kind of use these modern neuromorphic architectures and actually finally scale up these problems and sort of use this idea of physical computation to really solve these NP-hard computational problems.
By the way, Paxon, you guys know that there's this DW Chang? That's the same Dave Chang who built this ball that the mice run on, that Mike Schrecker uses. That's the same Dave Chang that turned to neuroscience after this. And built this virtual environment for the mouse to run it.
It's this very same David Chang. Yes, David. So then, a lot of my research then kind of has been addressing like the possibility of scaling up and using neuromorphic hardware to pose and solve these problems. And so I'm going to kind of go over these three different areas about trying to take advantage of neuromorphic hardware to scale up these types of computational systems. And so first kind of topic will be talking about spike timing codes. And then I'll talk a bit about these vector symbolic architectures and creating a sparse variation of these vector symbolic architectures and taking advantage of sparsity. And then I'll also be talking about the use of higher order interactions and going beyond the conventional energy landscape models and using these higher order interactions to also perhaps make these computational problems more efficient and feasible. And so I was a neuroscientist by training at UCSD, and when I came to Berkeley, I, of course, wanted to still work on neuroscience and develop theoretical neuroscience. And one thing that's extremely common in neuroscience is these place cells. And so if you record from a mouse's hippocampus and let it run around in the box, these neurons will fire whenever the mouse is in a particular location. So this is the mouse running around. And moreover than that is there's this very prominent oscillation called the theta cycle that goes on while this is happening. And the action potentials that are recorded during the theta cycle are locked in phase to this oscillatory cycle. And so it seems that the brain does take advantage of oscillations and spike timing to encode and represent information. But there was like a lot of problems with our theories about spike timing codes. And of course, there's the very conventional idea of rate coding and just turning a real value number into a rate of spikes. But there are problems with this just in terms of how much information you're representing per spike. It's very low. And so then there were a lot of proposals to use spike timing codes, but generally the previous work on spike timing codes were quite brittle because often just slightly adjusting spike timing codes causes it to noise to accumulate and the information to diffuse. So we kind of like realized though that we could think about the relationships between spike timing and oscillations to create a new type of spike timing code. And essentially the idea is that we can formalize a spike timing code in the context of a background oscillation as a complex value number. And so if you think about just a population of neurons as just being complex numbers, so then these are little phasor numbers, and you make a complex neural network, you also have complex synaptic value weight connections. You can directly translate this into a spike timing code, where essentially in the context of some sort of background oscillation, the timing of the spike indicates the phase. And then similarly, when you think about these complex valued weights, you can actually directly translate the phase of the weight into a synaptic delay. And so then by essentially just combining synaptic delays and oscillations and spike timing codes, you can build spiking neural networks that will implement this complex matrix algebra.
But they're not normalized complex numbers. They have a magnitude and a direction, right? Magnitude is the weight.
So
you're going to explain that further, right?
The magnitude of the weight is just an amplitude.
The magnitude of the complex number.
The magnitude of the complex number and the weight is just an amplitude, like a current injection. But then the phase is a delay.
Okay.
And so what we were then able to do to make these spike timing codes more robust is put them into the context of the very same attractor networks that Tank and Hopfield were using to solve these traveling salesman problems. And essentially, yes, the idea is you, of course, store patterns as basins of attraction and these energy landscapes, and but you can directly extend this into the complex domain. And basically, you essentially have the similar type of learning rule, but you kind of have complex conjugate here. And then you have, again, like a threshold nonlinearity, like they have in the original work. But basically the way it works is essentially in the complex plane, if you're below a threshold around the circle, then you are quiet. And then if you go above the threshold, you send a spike. And again, the timing of the spike would be the phase of the complex number. And so then you can just define then an attractor network like this, and it has an energy landscape, and we'll follow the dynamics to settle into this energy landscape. And then you can convert this using the connection that I was just describing into a spiking attractor network. And we made this variation of it that was a little bit more biologically plausible, where we have just standard integrating fire neurons as the excitatory population. And there's a single inhibitory neuron that acts to regulate the population. And essentially by kind of combining the excitatory inputs with this inhibitory input and the time constants of the cells, you can induce an oscillation in the cell's membrane potential. And then by tuning the delays according to the weights you store with the learning rule, you can store all types of patterns in the energy landscape. And then if you initialize the network to say some overlapping patterns like here, and let the dynamics run, the network will eventually find one of these local minima and settle it into the attractor state. And
Excellent. So in your previous formulation, why did you choose the weight matrix to be positive definite? I understand it says an energy, but you chose the variables to be complex. Why not choose the WIJ to be a complex matrix as well?
it is complex.
But it's Hermitian, right? So because you are making it positive definite.
What's that mean, Hermitian?
So conjugate, you're using.
It's a conjugate of different J, right? This is an outer product. Yeah, this is an outer product.
Okay, so WIJ has complex values. But
Yes.
There's still positive definite matrix.
It's still a positive definite?
No.
It still has real eigenvalues that and then positive.
I don't think so, because you put them on top of each other too.
No, but because if you're choosing an outer product of that form, it means it is positive.
Maybe, but yeah, it's complex value. Yeah. Yes. So then, right. Yeah. So then, track networks. But in the paper, we also describe an alternative way to implement the same idea using resonating fire neurons instead of integrating fire neurons and delays. And so yeah, the advantage of this variation is that you don't need delays, and often synaptic delays, especially on neuromorphic hardware, are pretty expensive. And so here the difference is now our neurons are resonating fire neurons, so they have two state variables, and it's basically just a harmonic oscillator. But then since there's two state variables, you can actually have these complex valued synaptic weights, where instead of just activating one, adding to the voltage, you can add to the real and the imaginary part of the state space and create these complex valued weights and get rid of the delays. But then still have the same kind of spike timing code. And what's cool about this too, and what we do in this other paper is show how this is an easy way to do kind of conventional signal processing on hardware like Loihi. And also then in this paper, we described that in Loihi, or in Loihi 2, we have access to what we call graded spikes. And so instead of the spikes being 1 or 0, which would correspond to the complex numbers having 0 or 1 amplitude, we can encode actually an amplitude into the graded spikes and then have arbitrary complex numbers. And then this allowed us to do like a little motion processing algorithm. So this is the Adelson and Bergen model. And what you can do is formulate these kind of GABA receptive fields in the complex domain, and they actually are motion filters. And then by just sort of streaming the inputs through these filters into these resonating fire neurons, they'll naturally do motion processing and things like that. So this is an easy way to potentially do these types of computations with resonating fire neurons. Okay, so then that's just my timing code stuff. And then when I originally went to Berkeley to study neuroscience, I was interested in this idea of binding and, trying to figure out how to address some of the shortcomings of theoretical neuroscience. And so the binding problem has been a really long-standing problem. And in conventional connectionism, we often think about a single neuron representing a particular concept. And so we have a triangle neuron, we have a top neuron, we have a square neuron, we have a down neuron. But early on, they realized that there is this problem, which they call this superposition catastrophe. And if you take these representations and sort of add them together, you get this situation where the connections between triangle and top and square and bottom are lost. And so this was kind of a problem for connectionism in theoretical neuroscience for a long time. And the same kind of problems occur in linguistics and doing symbolic processing with vectors. And but then that's when they discovered these ideas about vector symbolic architectures and how they can be used to actually address these issues. But there is a kind of actual straightforward way to use what I would call conventional connectionism to solve the binding problem. And this is described by Smolensky's tensor product bindings. And essentially, if you want to represent a conjunction like the triangle at the top, then you actually are going to take the outer product of your neural representations. And so now there's a triangle and top neuron. When you do the outer product, there's a neuron that represents that particular combination. And so then that allows you to deal with these conjunctions. But of course, the issue is that now your representation dimensionality is growing. And a lot of connectionists didn't really like this. Smolensky likes it, and it's not a problem. It's just, we have to pay this price. But then what I would point out is that in vector spaces, we can think of like an analogy to Boolean algebra. And essentially our matrix product is like the OR of Boolean algebra. And the tensor product is like the AND. Sorry. And the important thing about the and the tensor product is that it's a proper multiplication. And what this means is the essence of being a multiplication means you have the distributed property. And the reason that's really important is because of the relationship between multiplication and combinatorics. And so again, like because of the outer product, you get this combinatorically expanding representation. But you have a combinatorically large number of things to represent. But then this is where vector symbolics kind of came into the foray. And Tony Plate was a student with Jeff Hinton in the 90s, and they were working on this concept of a reduced representation. And what he realized is that you can take advantage of this idea of random vectors to represent bindings in a fixed dimensionality.
What factors?
Random. And so the idea is partly that if you take random vectors and you do their dot product, and they're very high dimensional, then your dot product will be very close to zero, meaning they're very close to orthogonal, just like the original connectionist vectors. And by defining this binding operation, so in this case, we have vectors of like +1s and -1s, and all we're doing to bind them is just a Hadamard product. And you can easily show that this will have similar randomized statistics. But then this means that it will be its own quasi-orthogonal vector. And so every combination of products will have this property. And so you can use these quasi-orthogonal vectors to represent this combinatoric space. And the reason is that essentially in some n-dimensional space, you of course only have n orthogonal vectors, but you have an exponentially large number of quasi-orthogonal vectors. And then over the years, there were various flavors of these that got invented sort of independently, but we're now kind of realizing that they're all connected and have similar properties. And there's very importantly, like complex value variations. And so then what this allows you to do then is do things you would do in conventional computer science. And essentially then by combining the binding operation with addition, and sometimes this other permutation operation, you can create essentially data structures in fixed vector representations. And so here's just like some examples how you might create data structures, and then they develop this like algebraic framework so that you could manipulate these data structures and do sort of conventional computer science. But of course, like there is a cost to this. It's not magic. And as you put more items in superposition, so as you add more items together in these data structures, there is this phenomenon of crosstalk noise. And so we developed this theory though to pretty precisely characterize the cost of the crosstalk noise. And so essentially this is just saying like, as we put more items into superposition, our ability to read out the data structure goes down. But as we add more neurons in our neural state space, we can add more and more items. So we have a whole long theory about this. And then we also showed that this capacity result is the same of all the various flavors of vector symbolic architectures. It doesn't matter if you do +1s or -1s or complex numbers, you always get the same kind of thing essentially because of the central limit theory. So as we were like working towards trying to implement these things in neuromorphic computing, we realized that one of the things that we want to take advantage of is sparsity. And so, of course, if you have a vector of all +1s and -1s, that's a dense representation. And so on an architecture like Lovihi, that's pretty expensive. And so then we developed this, we wrote this other paper where we show how, again, the tensor product binding is actually directly related to the various types of vector symbolic architecture binding. And essentially all of them are just reductions of the tensor product. And so Tony Blake, his original formulation used circular convolution. And mathematically, this is just like taking the tensor product and then adding certain elements together. And this bipolar representation, well, you can think about it as a tensor product, but then just taking the diagonal elements. But then to make a sparse derivation, we realized that the best way of doing it was to formulate it into this block code. And so essentially, now our randomized vector representations are broken up into blocks. And so every block has a single active element. So then there's k blocks, that gives you a k sparse vector. But then to bind vectors in this formulation, you have to kind of do a local circular convolution block by block. But this has really nice properties because it scales again linearly, whereas this one scales quadratically. This will scale n log n if you do the Fourier transform. And this, so then that also scales linearly. And it also is sparse. And so we've been working with this new sparse block code to then try to implement these on the chip.
But Paxon, this convolution is usually used for convolutional neural networks. You're not talking about that. You're talking about like for signal processing convolution, or what is convolution actually doing? What's the useful operation here?
Well, it's just that if you have these randomized vectors and you convolve them, you get another randomized vector. And so it's a quasi-orthogonal vector. It has this property of the same randomization property. So you just get a different vector that points in a different direction. You can use to represent your conjunction.
Usually what they call defining two different concepts.
Okay.
Like for example, your image and your control. That's the operation, right?
Right, yeah. So this is just like, the convolution is just a binding operation in this flavor of ESA.
Okay.
Whereas in a different flavor, it's this element-wise product. And then in the block, then you do combination block by block.
I don't know what those green and red triangles mean or anything. I think that's something.
It says these are out of the active neurons. The white neurons are active here. Okay. But okay, so then as we are exploring these different vector symbolic architectures, we also came across this really interesting idea that a lot of people in the field are now using. So in one of these flavors of vector symbolic architectures, you have complex numbers. But again, if these V's are just these phasor variables, you have element-wise products as the binding operation, right? And so if you just bind two vectors together, you can think about that as V squared. And then every entry of these vectors is like a phasor, complex phasor. And so in reality, you're just kind of spinning the phases, these complex numbers, right? But in the complex domain, you can do this fractionally. So we can define then like what we like to call fractional binding. And so then you just spin the phasors again proportionally to this continuous valued exponent. And what that allows you to do is then define a continuous domain and this concept of a continuous binding. And essentially what that does is induce a similarity kernel. So as you change this value in a continuous manner, you get this shape. And so essentially small deviations will stay similar, but then once you go a certain distance, the vectors become dissimilar.
What's the delta X then? What's the axis mean?
The delta X is like what's in this exponent. So the delta X is like from this original V to the delta X compared to V. Yeah.
You do that for element-wise operation? Like how do you multiply but not by multiplying?
You just spin the phase.
Yeah, just some of those guys.
So you like
phase less.
Right.
Okay.
Yes. Or, yeah, you can think about like just taking the angle and multiplying it.
Oh, I see.
And what we've realized eventually, though, is that there's this very famous and important paper by Rahimi and Recht called Random Features, but Random Fourier Features. And actually, the transformers use this trick. So the position encoding in transformers is based on this paper. And it's actually been directly mathematically connected to what we're doing here. We just realized it after the fact. But actually, Tony Plate described this in 1993. And what we also show in the paper is that you can then extend this to higher dimensions and do things like create topological structures. So we could do something like take an image and encode it into a vector by essentially taking the pixel values and multiplying it by these vector representations that represent the pixel location. So then you add this all up to a vector. This is a representation of the image. And then what you can do is translate the image by binding to this vector representation. And you just follow the math, like these exponents just distribute, and it leads to the image being translated. And then if you decode this translated image, you'll see the translated image. And then in this particular case, I've also created these vectors in a way such they have this circular topology. So then when things get translated off the right side, they come back to the left side. Or it's toroidal topology. So yeah, so then Rahimi and Reck basically, again, describe this, and again, this is part of the transformer literature, and they use this to encode the positions. But then what we also show in this paper, again, is how you can shape the kernel, how you can create higher dimensional spaces. You can use this in the context of the rest of the VSA algebra, and you can, again, make manifolds. And so it all depends on how you choose these random vectors, but depending on the probability distributions that you choose these different random vectors with, we get different kernel properties. Okay, so then that's some stuff about vector symbolic architectures. And then the other idea that we stumbled on, I guess, is this idea of factoring. And it comes up in VSAs a lot, but it's also just a generally important problem. And we kind of started with this issue where we have this vector S, which we know is the product of X, Y, and Z, the bindings of X, Y, and Z. And we know the possibilities for X, Y, and Z, but we don't know which one. And so then we're given S, and we're given these code books for X, Y, and Z, but we want to figure out which ones these are. And this is essentially factoring S. But then when we have, say, 100 options for each of them, we have this big combinatoric search problem that we have to solve. So 100 to the third power. And we kind of realized that there's this concept of searching and superposition that VSAs allow you to do. And essentially then this led us to develop this recurrent neural network architecture that we call the resonator network, which has these higher order multiplication operations inside of it, as well as essentially what amounts to the Hopfield attractor memory. And essentially the idea is that you create these neural populations that are guesses for each of the factors, and then you can use your guesses to infer so you can use the guess of X and Y to infer Z by unbinding S. And the idea is you can put like all of the guesses in superposition, and then the distributed property of the multiplication will distribute throughout. And so you could put thousands and thousands of guesses into this query, and then do this inference. But because of the crosstalk noise, you have a lot of noise in the inference stage. And so then the next step is to essentially use the code books to clean out this guess. And so then you get a better guess for Z, and then you use this new guess in another iteration. So then you build this recurrent neural network structure and just cycle through this process over and over, and it eventually solves the problem.
So do you use a linear Hopfield network? Like what type of Hopfield network are you using between the?
Yeah, this is all just linear. And then there is this one nonlinear function here, potentially. It could just be normalization, or often it's like put it back to +1 or -1, stuff like that. But then this is just like the linear Hopfield outer product rule. But it's not exactly a Hopfield network. So then, so here's eventually how we kind of like to visualize the network. And so then here we're given the problem of S is made out of X, Y, and Z. And then we have a neural population of about 2,000, and we're searching over this 1 million combinatoric space. And so then what the resonator network does, so this is iterations going on over time, and I'm just reading out sort of what it's thinking its guess is. And so eventually it starts off just randomly bouncing around in this huge combinatoric space until it sort of has this like moment of insight and rapidly converges to an answer. And then you can just tell that it converges and stop it and then read it up, and that's the answer. And then we have this paper again where we characterize its performance, and We couldn't find any formal proofs of convergence, but empirically, we just found that there is essentially what we call the operational capacity. And so essentially, as long as the combinatorics of the problem are less than the operational capacity, which if you make the network bigger, the operational capacity goes up quadratically, then yeah, the network's going to work almost every time.
But what is the m-axis?
This is the combinatorics of this problem.
Yeah, but I don't know what that means.
So it's like how many combinations are in the problem. So like, so we add, if you have 20 options for each, then it's 20 times 20 times 20, right? So that's over here somewhere, right? 100 times 100 times 100, it's a million, right? So we just give the network different combinations and see if it solves the problem or not. And then just empirically, it works as long as it's below this capacity.
I mean, is it like the hot-built network where you have to stay far away from the capacity and you have to make sure, like, you can only store practically, even if the vectors are uncorrelated, you can only store practically like 10% of the theoretical number of 0.18 of the number of units. Like if you have 100 units, you can store 18 memories.
No, so Toby, there was a talk by Dimitri Kotal.
Oh yeah.
And he was talking about that you can exceed the limit now, but you can only
Okay, this discussion of capacity dominated the whole field for about a decade.
Yeah.
Which to its great detriment.
Right, but this is a bit different. But I mean, it's the same point, but
Coding fast.
Right.
yeah.
It's just called okay.
Decoding.
Why does it converge faster again?
Oh, so what happens here is like basically once you start to just go over the capacity limit, it starts to just chaotically go on for forever. And so it just looks like it just goes on for forever. It never stops. But then once you like go on even worse, what it does is just converge really quickly to the wrong answer. So it just like gets stuck somewhere.
So if a pattern is not there, if it's not stored, what will it return? Will it return something which is a superposition as well?
Well, in a sense, if you give it an S that's not made out of the factors, it will either not work depending, but it also can combine and add the factors and it doesn't have to be, it doesn't necessarily settle to a one hot solution. And so then it will try to fit some combination of all the factors together to try to explain it. But it depends on a lot of different things in that context. So then what we've been doing since this is then trying to use this idea of generative modeling to formulate certain problems. And in my view, a lot of problems in perception are actually these types of factorization problems. And so here I'm just creating this simple generative model of a scene where I'm encoding, these letters as these vectors. And then what we can do is just place the letters in the scene by translating them with these translation vectors and giving them colors as well. And so this effectively is then a generative model for a scene like this. But what you can see is actually a bunch of these products, the sum of a bunch of these products. And so we can then ask the resonator network to factor a scene like this. And what it will do is try to figure out each individual object that makes the scene. So again, we essentially have a module for each of the factors, and it uses the inferences from the other modules and does a cleanup to make an estimate. And we put it through this recurrent neural network structure. And so this is sort of like how it behaves. So kind of we'll randomly hone into one of the objects in the scene and solve this factorization problem. And then so the peaks of these different bar graphs are indicating the answer that it comes up with. And then here I'm just visualizing the dynamics at the time. And so then we're essentially trying to say that like You know, translation invariance is a big problem in deep neural network literature. But here's an alternative way of just viewing it. And, you know, you don't really have to then do any training. This is just formulating a generative model and inverting it. And so I think this is a powerful way to kind of pose different perceptual problems. And what we've also been doing then with Alpha is using this framework to do visual odometry, or it's kind of basically SLAM. So then the idea is that there's like an event camera that gets encoded into an image. And we were able to also include translation and rotation into this generative modeling framework. And so this resonator network is then going to try to use this internal map it's forming of the scene and register kind of the current input onto effectively this allocentric map. And so then, it solves the problem, and we then add sort of a re-registered image back to the map, and it kind of accumulates this map over time. Very SLAM-like. But then you're able to kind of use this data set, familiar to some of you, but essentially, where just the DVS camera is panning on these images, and we form this internal map from the input, and then use the resonator network to figure out the translation and rotation that's being applied to the camera. And then the last little thing I'll mention is we've been putting some effort into also trying to do semi-prime factorization. And so, of course, like in cryptography, semi-primes prime numbers are like the key to how cryptography works. And effectively, if you want to crack a cryptographic code, you essentially solve a semi-prime factorization problem. And what we realized is then we could use this exponentiation trick to encode values in a vector in a way that like we can formulate it as a factorization problem. So basically, we're given a semi-prime S, and then we just take the log of S, and we put this into the exponent of our hyperdimensional vector. There's like one little coefficient here that you need to add, but so you just make this a really large number. And then if you just kind of follow some math, you can see how then this representation of the value of S actually is the product of its factors.
But isn't it very sensitive to, it doesn't have to be extremely precise to actually do factoring? Like, you're trying to factor two very high resolution numbers. As soon as you go into the M1 domain, how's that possible? It can work. Am I missing something? It's not approximate factorization. It's like you have to really get the numbers.
Yeah, but I mean, it's just that when you put these numbers into the vector, the
number is encoded as this high dimensional vector.
Right.
Where's the log then?
So like you have here the number 600,000, right? 329 is a semi-prime.
Okay.
Take the log of that. That's
some precision.
Well, to some precision, yes, but it doesn't really matter that much. I mean, you need some precision. But then you do this exponentiation trick, right? So then you're going to multiply. You take a random phasor vector, right? You multiply the phase value angles by this number. And that's just the representation for the semi-prime, right? But this is also the equivalent way of expressing it, right?
Well, what if the number is a practical number with like 300 digits? Not 6 digits, 300 digits. Aren't these numbers that are used in real encryption like immense numbers?
They're immense, yeah. I mean, they are immense, yes. Yeah. Right. I mean, I'm not like saying P is equal to NP, right? But like, there's still like, it's still a hard problem, but you can formulate it this way.
Okay.
And you're right, there is a precision issue, like there are precision issues. But this is all just floating point numbers. And,
okay.
But then basically, yeah, you can then essentially, you fill out your code books and the resonator modules with these logs of primes.
Logs of primes, okay.
Right. So then in these code books are all the prime numbers represented as vectors. And then if you give it as input this vector, it will solve this factorization problem.
But the code has to be immense then, right? In reality, it would have to be immense.
It's pretty big. I mean, yeah, I mean, there's a lot of primes, right? But you know, the number of primes is sort of logarithmic with the number, the size of the number. Yeah. So
And the same precision arguments also hold for quantum computing, right?
Yeah, sure.
So the sure rate will not work if there's noise.
You're saying you don't have to actually be so precise because the density of primes is so low.
right, because the numbers, the vector representations of these primes they don't necessarily look like each other.
Okay.
And if you know, if the vector is like slightly off, you know, from the precise number, it's still like it's going to have a higher product.
Okay.
And so it doesn't have to be perfect.
I see.
Cool. Okay. I mean, and then, so then basically now, you know, I've been working with Luigi too, and you know, we're finally getting to the point where it's actually working, and we've been fleshing out like a bunch of new types of neuron models and new types of connections, and so we're coming out very, very soon with a new update to our software, which will have things like resonant fire neurons built in, and things like the sparse binding, and hopefully then we can really like see if we can put these ideas together onto the real chip and actually make it pretty large scale. And then I'll just also advertise that Intel will be having a workshop in a couple of weeks. So then we'll have this new release of the software, and we'll have a bunch of talks that are basically online and for the public on July 20th and 21st. And then if you're part of our community, you can come to Santa Clara on the 25th, and we'll be in person and working with you and showing you all the new fun stuff. Cool. Is there any other talk? Thanks for staying around, guys. Some questions.
What's the sign on Logi? So you have table.
The sign?
Yeah.
Sign and cosine.
So for the resonant fire neuron, basically you basically, you know, it has parameters like its frequency and its decay, and so then you just calculate this first, you know, and then there's just a constant. So this is just a constant that you put into the memory, but it's all like in fixed point representations. And, but yeah, you just like this is fixed once you instantiate the method. But we also, the other thing is we are using like Taylor expansions to do nonlinear functions. So it's another thing we're working on a little bit. It's like if you want to put some nonlinear activation function on the neurons, you can effectively use some Taylor expansion tricks to make nonlinear functions.
You can also use to integrate prime neuron phase log them to create this resonant correlation antipode. So you can have an excitatory and inhibitory connection to create a phase log.
I mean, probably, yeah, probably.
Hi, I have a question from Zoom.
Sure.
Okay, I have a lot of questions, but I'll try to minimize them. I'm interested in a complex recurrent networks as well, but when I was reading kind of their connections to the Zigovich model, and I don't know if you're familiar with polynchronous groups,
Yes.
they talk about how the phase of the spiking of the complex number is not exactly equal, like one-to-one mapping to timing coding in the brain. They said that it can sort of simulate synchrony, but it can't simulate exactly all of the timing effects that we get. Do you have any thoughts on that?
Wait, so, well, the Zigovich model isn't like directly linked to complex numbers.
So he that was a bit of a tangent. He talked about polychronous groups, and this is sort of a separate paper. I'll try to find it if I can. They made the suggestion that complex values can't perfectly simulate the timing effects of timing coding in actual neurons. Is that something you agree with, or do you think that the complex encoding actually can encode all the timing encoding that we need for simulating neurons?
Well, yeah, so polychronization is very similar to the spike timing representations in the TPAM network, but they're different mechanisms. And effectively, the polychronization is just about like precise synchrony, but it has this like brittleness if like the phases aren't perfect, or like the timing, if the timing gets adjusted a little bit, then the precise synchrony can break. In the brain, I mean, the TPAM can produce arbitrary spike patterns, so it can encapsulate whichever patterns, but then there are a lot of weird things that the brain does that you wouldn't necessarily see in TPAM. So like in the hippocampus, what happens is as the mouse moves through its place field, the phase relationship between the theta cycle and the spike timing changes over time. They call this phase perception. And so we can actually encapsulate something like phase perception by combining the spike timing code with these fractional power codes. So if you just encode the position like a fractional power and then move it around, we'll see phase perception. But then you'll also see phase recession, which you don't actually observe in the brain.
Oh, okay, thank you. And so, second question: how you're probably familiar, but what you talked last was sounded very similar to me to disentanglement in neural networks. Do you see any connection between sort of the deep learning models of disentanglement and what you're trying to work on now?
Oh yeah, definitely. I mean, effectively, factorization and disentanglement are just synonyms. But then the issues a lot with the deep learning things that we faced. So we have like been applying deep learning to these scene analysis problems and the other combinatorics problems. But the reality often is that you need the deep network to be exposed to the full combinatoric search space. And if you leave gaps in the training data, then the network won't just generalize these gaps, and it will have these gaps in as a kind of a prior. So like we did these experiments where we trained the network on the simple scenes, but we never showed it a 7 in the bottom left, and we showed it other numbers in the bottom left and other 7s in the rest of the scene. But if you at test time show it a 7 in the bottom left, it will never output that it's a 7.
Okay, I'll hold off on further questions. Thank you very much.
Sure. Other questions. So, we do now have this other capabilities, right? You mentioned those resonant fire neurons, right? Mm-hmm. So what are the? Can you give us a feel of what are the features of LoE2 that will enhance the way we can do neuromorphic computing more generally?
Definitely. So, I mean, LoE2 has a lot of just basic improvements over LoE1 in terms of like how dense it is and how much you can connect things. But also what LoE2 has that we're sort of reluctant to expose to the public is this microcode engine. And so there's basically a programming language inside of LoE2 where you can almost do any type of neuron model that you want. And you can do a lot of other crazy things in this microcode language. And in this next release, I built a lot of microcode file neuron models for doing resonant fire neurons and also just doing graded spike computations. And so we'll be able to do just kind of normal linear algebra with these graded spikes. And there's just like a couple of new neuron models that you'll have access to in the next release.
So we'll make those available to the community.
Yeah.
But others may not be able to do their own microcode.
Right. So we're not yet ready to let others do their own microcodes, but I'm trying to get it out in my beta public, and because also it goes on, what you can do in a microcode goes way beyond like conventional computational neuroscience. And so I think like once you start to see it and use it, there's a lot of kind of weird things you wouldn't necessarily think of that you can do in YouTube now.
Great. More questions? Thanks so much.